To determine the graph of the cotangent function, we can follow the same process that we did for the tangent function. However, we're going to use this opportunity to explore graphing reciprocals of functions. Graphing reciprocals is not difficult, but it does require a little bit of thought to understand it. Before we can get into the graphs, we just need to think about reciprocals in general. The reciprocal of x is 1 over x. If x is very large, then its reciprocal is very small. And if x is very small, then its reciprocal is very large. Specifically, if x is greater than 1, then the reciprocal is between 0 and 1. And if x is between 0 and 1, then its reciprocal is greater than 1. Negative values behave similarly. The only values that remain unchanged when you take the reciprocal are plus and minus 1. When it comes to graphing reciprocal functions, we have another property to add that is just an extension of this. If f of x has a 0 at some point, then the reciprocal function has an asymptote there. And if f of x has an asymptote, then the reciprocal has a 0. With these ideas in mind, we can now graph the reciprocal functions. The cotangent function is the reciprocal of the tangent function, so we will start with the tangent function. First, we will copy the relevant information from the graph onto a number line. We need to keep track of the locations of zeros and asymptotes, as well as keep track of whether the tangent is positive or negative on the various intervals. We will now make space on the graph to draw the cotangent function. We need to turn all the asymptotes of the tangent function into zeros and all the zeros into asymptotes. This information can then be placed on the graph. The numbers plus and minus 1 are fixed points under the reciprocal, so we will mark these as well. To determine the behavior of the cotangent function near its asymptotes, we just need to look at whether the tangent function is positive or negative there. Since taking the reciprocal does not change the signs, this will tell us whether the function is approaching positive or negative infinity. Once we have all of this information, we can create the graph by simply connecting all these ideas together. This has a very similar shape to the tangent function, except that it has been flipped and shifted. It is important that you recognize the steps involved when graphing the cotangent function as the reciprocal of the tangent function. Specifically, you need to understand how the roles of zeros and asymptotes switch with each other, that signs don't change, and that plus and minus 1 are fixed points. The fundamental cycle for the cotangent function is 0 to pi, and here is the chart of key values. The process of graphing transform versions of the cotangent function is similar to the process we've already developed and practiced for the sine, cosine, and tangent functions. Example: graph y equals -2 cotangent of x over 4. We first determine the fundamental period by setting the argument equal to 0 and pi. This shows us that the fundamental period will be the interval from 0 to 4 pi. We break this into subintervals and get that the key values will have x-coordinates 0, pi, 2 pi, 3 pi, and 4 pi. We can then calculate the y-coordinates by substituting for the trigonometric function. And then we can put these pieces together to get the graph. As you can see from this video and the previous one, the technique of graphing using key values extends beyond just the sine and cosine functions. We've now seen how to graph both the tangent and cotangent functions using the exact same ideas. The fundamental periods are different, and the shapes of the graphs are different, but the ideas carry forward. In the next video, we will look at the graphs of the secant and cosecant functions.